Hi everyone, and welcome to the lecture that will cover how we measure metabolic activity. Now, this will be a little bit supplementary to your lab section where you're going to be covering this topic in greater detail, and actually the lab will be a virtual version of actually measuring some of someone's metabolic activity, but we'll dive into that at that point in time. For now, let's get you some background information and some working knowledge about metabolic activity to get you started, okay? So first off, it's important to cover two categories, if you will, or two types of metabolic measurements that we can do. One is called direct calorimetry, and the other is indirect. So when we look at direct calorimetry, I'm actually going to pop over to the diagram here in brief. So what we'll see is we have a closed it's a closed system. So for example, heat, air, there can be no exchange except for what's in there and what gets exchanged in there. And now the great thing about this is, for example, the heat given off the person exercising here, as well as the air breathed in or the carbon dioxide breathed out by this person while they're exercising, is completely contained within the system. And we have this insulated with water, and through that water, what we can do is measure a change in temperature. So the amount of heat that this person gives off during exercise is one form of energy conversion that occurs. So when we metabolize food, we use energy, and some of that energy gets lost through heat. Actually, a lot of it does. So we need to capture that as one form, but we can also measure the amount of CO2 that comes in, as well as the oxygen provided and used by our cyclists here. So to be a bit more specific, aside from the overall image of what goes on in direct calorimetry, we'll know that direct calorimetry uses heat production to measure a metabolic rate. Okay, so the amount of heat given off is measured in that water, and what we say is the unit itself, kilocalorie, or big C calorie, not little c, but a capitalized calorie, as written here, is the amount of heat energy required to raise the temperature of 1 gram of water, so it's a fairly small amount of water, by 1 degree Celsius, okay? It's a very weird definition for how to define what a particular unit is, but kilocalories, that is the exact definition. So when you're reading the side of food that has nutritional information there, and you see something has 10 kilocalories or 10 big C calories, what it's really saying is it has 10 units of heat energy to raise a gram of water by, in this case, I guess it'd be 10 degrees Celsius. Kind of interesting, kind of wild, hey? So again, direct calorimetry is this closed system. It has this water, they call it a water jacket, but essentially water walls that will absorb the heat energy, and we use the change in temperature to determine directly how many kilocalories are exerted by that individual for that activity, okay? And a calorimeter, just in general, I should probably have mentioned this right off the top. I mean, this happens, we have calorimeters in science, generally speaking. So in chemistry in particular, or physics, if you're trying to measure the heat of a chemical reaction that's been conducted, what you'll have is a form of a calorimeter. They usually call it a bomb calorimeter, or there's kind of a homemade version you can do too with styrofoam cups. But maybe you've done that in lab in high school or first year university in one of your science labs. But yeah, so that's all it is essentially some means of water to absorb heat and hopefully as close a system as possible. It's not always airtight, but as close as you can to try to get an accurate measure of the heat exchange that occurs. Okay, so I've said that about 3 or 4 different times now. Heat exchange, heat given off. So that is the key when we're talking about direct calorimetry and what a kilocalorie is, or a capital C calorie. Okay, so kcal, capital C calorie. Okay, moving forward, indirect calorimetry. So if we zip forward to the next photo here, or a couple of slides ahead, you might recognize this from movies, or you see it's like the sports montage of the team like getting fitter, and it's like classic if you watch if you've seen one of the Rocky movies where Rocky is just kind of like grassroots sort of guy. He's like lifting logs and punching hanging meat in a butcher shop and like all this stuff. This is how he's doing his training, and it cuts to his competitor who's like very science-based, and everything's in a lab, and he's getting this sort of contraption done. Well, this is called essentially a metabolic cart, this whole thing. And this is typically what you'd use in the lab, and we do in the lab, but you'll see a virtual version of this. And this whole kind of contraption here is called a Hans Rudolph mouthpiece. And yeah, so you get set up on a treadmill or physical activity, stationary bike or something like that. And what we'll measure for indirect calorimetry, so you can pause right here, is going to be the gas exchange. So that's why you have something on your mouth, and most importantly, plugging your nose. So we know the only gas exchange that's happening between your body and the atmosphere of the world around you is through this mouthpiece, okay? And because of that, we can measure, what's being breathed in and what's being exhaled through this tube, and it'll pick up what's being breathed, okay? So you're probably asking yourself, all right, indirect calorimetry, how the heck does that happen? How do we take oxygen, utilize CO2 produced, and figure out what the metabolic rate is? And more so, it can actually even provide insight to whether carbs or fats are being utilized. How does that happen? Good questions. Wow. So, when we're talking about oxygen consumption, we're talking about rates. Okay, so that's the first important thing to understand, is the units we're talking about. Now, your textbook, so I want to put a little caveat in there. It'll give 2 ways of displaying rates, and they're both correct. Liters per minute or milliliters per kilogram per minute. And whenever you see something per minute, that's a rate. How much is something happening every minute, right? So it mentions here that when you don't carry your body weight, or sports that are related to that, like rowing or cycling, where you're sitting on something or in something and performing some exercise, a wheelchair would be another example, you use liters per minute. And when you're running or cycling uphill with body weight, or probably even like any other sport, soccer, etc., you'd use milliliters per kilogram per minute. Now, I might say practically as a clinician, you are generally, whether you're cycling on flat road or uphill or whatever, you would definitely use milliliters per kilogram per minute. It's more practical as far as including your body weight in there, because even if you're cycling on flat ground, you're still using your body weight to propel yourself, or you still have to carry your body weight to propel yourself, okay? Rowing is a little bit less, but yeah, so there is some differences, I think, practically in a research setting versus clinically, or in practice, what might be done. But generally speaking, the go-to, I would suggest, unit to use for oxygen consumption is milliliters per kilogram per minute. Now, we've spoke about oxygen consumption in some lectures previously, but what I didn't mention what we didn't use is a unit of measure for that, okay? So that's this unit of measure. But if you recall, a VO2, or we've spoken to it about as a VO2 max, that's the volume of oxygen maximally that can be taken in during exercise or for aerobic respiration there. Your oxygen consumption just in general can be expressed as VO2, or volume of oxygen, okay? And that's a rate. Again, that's a really important thing to keep in mind. It's a rate at which we're utilizing oxygen for or during exercise. Okay. Tried to say that a few different ways to help at least one of them land. Hopefully that sticks. But if we look at, let's look at two things. So this helps. We'll look at our respiratory exchange for carbohydrates and triglycerides, because that's where kind of our main metabolic substrates come from to make energy, right? So again, if we're putting back in context for the mouthpiece, we're trying to look at based off of how much oxygen we can take in, which will be at the bottom of this ratio. A ratio is just a fraction, really, versus how much carbon dioxide we expel relative to the amount of oxygen we pull in. We can see that roughly for every 6 oxygen molecules that we bring in, we expel or breathe out or exhale 6 carbon dioxide. And so when is this happening? Where is this when and how? Well, this is when we're metabolizing carbohydrates, in particular glucose. So if you go back to the metabolizing substrate lecture, you'll see this should look like a somewhat familiar equation. What we end up with is, you can see that once glucose gets metabolized, we get 6 carbon dioxide, 6 water, and 30 ATP, which should sound roughly familiar. I feel we also gave the numbers, about 32 or 33, depending on whether it's glycogen or glucose. Okay, this is a good ballpark. Now, if we metabolize triglycerides, what happens? Well, slightly different molecule that we're starting with, our hydrocarbon chain. So during this aerobic exercise, again, that's how we metabolize triglycerides primarily. You can see we have much more oxygen in and some carbon dioxide put out. So based off the biochemical processes versus when we metabolize carbohydrates versus triglycerides, we can see that we actually expend about 70% of the oxygen that we take in as carbon dioxide when we're undergoing aerobic respiration for triglycerides. So what does that mean? Well, we get this huge ATP output, and this ratio, when we calculate it out, ends up being about 70% or 0.7, right? And just to hop back here and finish the explanation of carbohydrates, if we have 6 over 6, that's a ratio of 1. So again, we'd express our RER as 1 for carbohydrates and 70% for triglycerides. And this is purely if only these substances were being metabolized, okay? But as you remember, that's not always the way, right? We have some carbohydrates being metabolized, some triglycerides, and depending on the activity or if we're at rest, that will vary, right? So what we end up seeing is we get some sort of a percentage typically that will be between these, okay? Not always, but typically. So for example, if we have a ratio or an RER of 0.85, means we're roughly metabolizing half of our carbohydrates and half of our ATP is coming from triglycerides, okay? Okay, right. Give you a moment to digest that. So again, these ratios is our metabolism, the amount of carbon dioxide we're exhaling over how much oxygen we're taking in, the ratio of oxygen used and CO2 produced, okay? Good. Now, I said most of the time our RER falls between these 2 points, but I did make a note when we were talking about metabolizing carbohydrates and very high intensity exercise. What did I say back in that lecture? Well, I said that occasionally you can get much higher than 100% or full metabolization of carbohydrates. And when we have that instant, you can actually see RER ratios. There's some research to support this as high as 1.15 or 1.2, okay? But after that point in time, again, the accuracy can be debated, okay? Great. So we'll just take a little quick peek here at a chart explaining our RER steps or ratios that we can see from about 0.7 to 1, and then it explains roughly how much carbohydrates versus how much triglycerides are being metabolized at that point in time, and the rate of energy, so how many kilocalories per per liter of oxygen is being produced. So for example, to speak to that, when we're about 50-50 carbohydrates and triglycerides, we see that we get about 4.86 kilocalories kilocalories per liter of oxygen consumed that is generated. So we look at that as energy, right? Even though we measure it as heat, right? It's still a form of energy that we're producing that allows us to do work. On the other ends, we see 100% triglycerides. Well, it's 4.69, and on the high end, when we're looking at pure carbohydrate metabolism, we're looking at about 5 kilocalories per liter of oxygen consumed. Again, that's a rate at which energy is produced based off of oxygen consumed. Okay. So how do these numbers kind of help? What can we use with this? Well, one example is we can figure out what type of fuel we're using when we're exercising, right? So if we're at a low energy expenditure, we're near that crossover point between say aerobic and anaerobic activity, or using different metabolic substrates, we can see these sorts of this ratio. Or if we're purely giving an all-out effort, we'd see a RER closer to 1. But what if we're not exercising? Well, we can use these numbers to figure out things like our basal metabolic rate and resting metabolic rate. What are they? What are the differences? Well, basal metabolic rate is our metabolic activity that we have when we're laying down on our back, so laying in supine, well into a fasting state, so 12 to 18 hours after a meal. Usually you stop eating at a certain time during the evening, and then sleep, and then once you wake up, you have your metabolic rate calculated, and we'll find that about 60 to 70% of our total daily calories from this fasting, resting, non-moving, recently woken state accounts for about three quarters of our total daily intake. Again, we'll chat about this more in lab, but remember, there's things like eating and walking around and exercise and a lot of other contributing factors that add to our metabolic rate or metabolic energy use in a day. Okay, so this is just during resting. Okay, and after a long fasted state, resting metabolic rate is a metabolic rate after about 4 hours after a light meal. So fully digested meal, so we know we're not accounting for any thermogenic effects that occur with eating. So if we eat food, our body will produce a little heat, becomes a little more metabolically active than if we were purely resting. And then again, after a long period of resting, we know our heart rate is going to get to a resting state, and we take our measurement then. Okay, and these things will change, again, age, sex, body temperature, stress, body surface area, and just generally weight and mass can be included in there as well. Those will affect what our resting and basal metabolic rates are. Okay, great. So again, we'll cover a lot more of this in detail in your lab, but what's worth going back and reviewing and really knowing is the respiratory exchange ratio in particular. How do we know, how did we come up with this exchange ratio, and what do those numbers generally mean? You don't have to memorize the chart by any means. Additionally, it's good to know what a kilocalorie is, what it measures, and what the units are. Okay, cheers.